So here we are. For the record, we were solving the easy category of questions for the systems of linear equations in two variables. And we made some progress on those. And my idea was to give you a sense of what we want to talk about today. Maybe we'll talk about the experience later. But now I would like to start by talking about some basic stuff. Perhaps now it's a good time to start sharing my screen. Then you should be able to see my screen now. Okay, so maybe I ask you now, how was the quiz or the exercises? This is a question to everyone. What do you think? Were they good? You think you did well?
I didn't finish, but I mean, it's a good exercise.
It's a good exercise,
Yeah.
right?
Same.
Yeah, because every time we spend time on the easy problems, I thought we'd switch things around a little bit. You guys do the easy problems, and then here we would do some more advanced problems. But then we first want to talk about the basics. So again, today we're going to talk about systems of two linear equations and two variables. And I would like to go over some stuff before we start. Oh, okay, that's my draft. Maybe you shouldn't see this. That's a very ugly draft. You see how you transition from this to that? Oh, wonders. So maybe I should erase that part. Then you didn't see anything. Yeah, so I have all of the exercises from the question bank here. Again, these are the exercises from the question bank, which are not available on any on any previous practice exam or on any past paper. And I think today we would like to do some hard problems, and we should be able to do so if we go over some prerequisites. So these are basically the skills and machinery that you'll be using to solve the questions. Now, without further ado, so it's the same setup. I mean, system of two linear equations, two variables. You would expect them to have. You expect yourself to have two linear equations, and you would expect each equation to have two variables. So that's a bit self-explanatory. But this form isn't really something we're used to seeing. So if we start with two equations that looks like this, then maybe that is a bit awkward for us. So just to skip the symbols, these are just symbols, they're just numbers. So I'll put in some numbers now. So maybe 2x plus minus y, so 2x minus y is equal to 4. That is a linear equation. It's not the usual equation where we have y is equal to mx plus c, but it is an equation. You could also have 4x minus 7y is equal to minus 17, and so on and so forth. So these are different types of examples. We're just getting acquainted to the shape of this object that we'll be dealing with. So it looks like this: a1 times x plus B1 times Y is equal to some C1. I'm numbering them to distinguish between the line J and the line K. These are equations of two lines. But I need to prove to you first that they are indeed two lines in our two-dimensional space. Because if I give you 4x plus y is equal to 7, then how do you plot this? And what's the slope? What's the y-intercept? These are the stuff that we're used to, but we don't see here. To prove to you that this is really our standard equation where we have y is equal to mx plus some constant, I just make a quick argument here. So if I take any ax plus by, which is equal to some c, which means I multiply x by a factor, I multiply y by another factor, and I have a certain constant, which is the result of the equation. Then I can just simply solve for y, because if I solve for y, I should get something of the form mx plus c. I mean, we can hope for it at least. So I just take away ax from both sides. I add the additive inverse, and then I multiply by 1 over b. So I get that y is equal to c over b minus a over b times x. And then this is very nice because we're actually done. So I just switch these two terms around, just commutativity. And then I have y is equal to something times x plus something, which is really just, y is equal to m times x plus some constant g. So I hope you're not confused. I hope you're convinced that this is actually just a line. It's just a line. Like no matter how complicated it looks, 1/2 of x plus 34y is equal to 257. It's just a line. That's all that it is. And we can find its slope. We can find its y-intercept. I mean, this is not really the core of what we will be doing. We won't be finding slopes and y-intercepts, but they are lines, and perhaps now you trust me more. And so if I just choose this m to be minus a over b, and I choose this d to be c over b, then I have an equation in y and x with a slope and a constant. That's all I wanted to say. Now, what do you think? Do you think this makes sense at least? I would really like you to say that it doesn't, because then we can have a good conversation about it. So maybe take a moment just to look at this. We started with something, so something times x and something times y, it's equal to something. And then we ended up with an equation of a line, which we are acquainted to and which we know very well, which is of this sort. So is this transition at least clear for you conceptually?
Yeah.
Okay, that's good. So I hope you believe that this is a line. So we have two lines in space. We have two equations, two linear equations. Then we have two lines in space. Now, what are the odds? So we have some initial equation that looks like this. We have some other equation that looks like this. And then we have two lines. So this is the first line. It's in purple. I think that's purple. And the other one is in brown. So there are really just three possibilities here. So if you have two lines in space, they either intersect once, or they always intersect because they're the same line, or they never intersect. And I think conceptually this is not too difficult to see. So this is what we have. We have some nice drawings, some nice colorings. Here I use the example of y is equal to x. So this is just an example. you can have any line that's in any part of the plane, and then you would have an infinite number of solutions. Okay, maybe I'm skipping parts, but what I will say here is that if we recall that this is actually an equation and a line at the same point, at the same time, then the intersection of the two lines is the solution to the two equations. Maybe I should say this again. The intersection of the two lines is the solution of the two equations. It's the point at which this first y, I should call this y1, y2, this I should call y1, where y1 is equal to y2, and x1 is equal to x2. So they meet once. They could also meet always. So you have a line and a line that's exactly the same. And we will talk about how this looks like, because a priori this is not obvious. Or you could have lines that never intersect. Now, before we talk about solutions, I just want to make a few brief remarks. One remark would be, if I look at the middle case, what can I say about the slope of these two lines?
They're the same.
They're the same. So Darren says they're the same. What do you guys think? Do you think they should also be the same? Remember, they're the same line. Yeah, I mean, Darren's right. Okay, and what about the constant? Should it be different or should it be the same?
Same.
The same. Okay, I mean, yeah, definitely should. I mean, these are literally the same line, so they should have the same slope and the same y-intercept, because the slope and the y-intercept define the line. They always define the line. These are the two defining properties of any line or any linear equation. Okay, and now I want to switch to the right for the case where they never intersect. So how would you make two lines never intersect? How do we cook up a recipe for that? First, I want to ask you about the slopes. So what do you think the relation between the slopes should be?
Yeah, the same.
They're the same. Okay, I think that was Flavia. So Flavia says they should be the same. Okay, but what about the y-intercepts? Do you think they should be the same?
No.
Yeah, but can you explain to us why, maybe?
I don't think they should be the same.
Okay, what happens if they are the same?
Then it's the same line.
Yeah, then they always intersect, right?
Yeah.
So if we play with this and we say C1 will not be equal to C2, then we have the opposite. We have two lines that will never intersect for one reason, because if you draw the two lines parallel to each other, so they have the same slope, then they will never intersect, because they are not the same line and they are parallel to each other. But if they are incident on each other, then this is the case where you have infinitely many solutions. So if that is not clear, please feel free to interrupt me. Here I use an example of y is equal to x and y is equal to x minus 3, for example. So these two lines will never intersect. Now going here, lines which intersect once. What can you say about those?
Everything is different.
Everything is different. Yes. So would you say that it would be any case which is not the other two cases?
Yeah.
So I think that's a good way to think about it. So if you look at it, so it's not any of the other two cases. So C1 can be equal to C2, that's normal, or it can be not equal to C2. I'm looking at these two statements in parallel. Okay, no, lots of parallel lines and statements parallel, but please bear with me. But can we say something about the slope? Well, yes, it will not be the same. That is for sure, because if the slopes are the same, then we have one of these two cases. And in the two-dimensional plane, these are really only the three cases. So if the slopes are not equal, then it must be the case that they intersect once, because it's not any of the other two cases. And do you agree with me that these are the only three ways that two lines can meet in two-dimensional space? Okay, see some nods. Yeah, okay, well, no objections. I'm happy. Then I can say, okay, then in this case, M1 will not be equal to M2. And for the intercept, really, it can be anything. So we don't really put a restriction on that. And now we talk about solutions to the system of equations. So I want you to keep in mind that we started this discussion with two equations, J and K, which are of this form. We transform them to this form by the initial argument, but when you see them, you'll see them in this form. Just to give you an example, maybe I'll go here. So this is an example. So 4x plus 2y is equal to 86, and 3x plus 5y is equal to 166. These are two lines in the plane. Just an example. Now back here, I would like to say some brief notes on the solutions and why this translates to solutions of the equations.
What's C representing?
Huh?
What's C representing?
C is the y-intercept.
Or
So you have an equation of the form of y is equal to mx plus c. And so this is what we're talking about when we mean m and c. So m is usually the slope, but c maybe. Some people use b, some people use d. So it's just notation. I hope it's not too obscure. Now, just a few words on the cases of solutions. So if the lines intersect once, then there is a unique solution to the system. Again, we start with the system of equations. We transform it, in our minds, to something that's graphical, and we look at the solutions. We see there is, well, not the solution, we look at the intersections. And when we look at the intersections, there's one intersection, which means there's one instance where x and y match. And since these two equations are in x and y, then there's one x and one y, which satisfies both of these equations. So conceptually, this is why intersecting of lines means x and y, which satisfy both equations simultaneously. The point is literally on both lines. So conceptually, I hope that is clear. If they intersect always, then you have an infinite number of solutions, because you have an infinite line with infinitely many points, which you can plug in to get values which satisfy both equations. Well, actually, both equations are just one equation, if you think about it. And if you have two equations which never intersect, then there is no x and y which satisfy them. And if there's no x and y that satisfy them, then there is no solution for these equations. Now here we're talking about this type of equations, but this is exactly equivalent to that one. So the x and y which satisfy this are the same x and y that satisfy this, and vice versa. So that is at least why this transition makes sense conceptually. So I'll write this note down, and then we'll start doing some exercises. So in this case, where they intersect once, we have one solution and it's a unique solution. And it's the intersection of the two lines. In this case, the solution is a line, and a line has infinitely many points. So we have infinitely many solutions. In this case, the solution would be, the equation for J, or the equation for K. Any point X and any point Y that you plug in will give you a solution. So maybe I will not write J's and K's, but this is the key that I want you to remember whenever you see solutions that are being discussed or lines that are being intersected. And finally, if they never intersect, then here there are no solutions. By solutions, again, we mean X and Y will satisfy both equations. Graphically, you can see there are no X and Y that satisfy both of these equations, and therefore we can conclude that the system is unsolvable. Now there is a brief transition, because all this time I've been talking about equations of this form, but I've not been talking about equations of that form. And so I think the best practice to do right now is to take a look at the sum of these. And I will not be doing the easy ones, because they are easy. I mean, I don't set the rules. And I would like to start with some hard problems. Because here we're talking about a certain different skill, a skill set that you need for this skill in the SAT. So you have a system of equations, and let's say you don't have decimals, or you don't have time to open decimals, and you would like to have a go at this question, you would like to solve it. Maybe you guys can get a minute, think about it, and then we'll think about how we can approach it. Because it's not anything guys discussed in the last 20 minutes, I think. It's 20 minutes. So we will talk about ways we can solve this type of equations. Yes. Go for it. Sure, you can do whatever you want.
Maybe you can add the two equations.
Okay,
so X cancels out.
Okay, that's another way we can do it. I would like you guys to try it out and see what you can get as a solution.
So Y is equals to 6/4.
Or 3/2, sure. Okay. That's Aciosius. A few more moments.
And X is equals to 5.
Yeah, sure. I mean, but the question is asking for Y, so you can just worry about Y.
Oh, I got the same answer. I thought we were looking for the X as well, but
No, so the question is asking for the value of Y. So that is what we're looking for. Yeah, I think time's up. Yeah, I think in the SAT you get like 60 seconds or 70 seconds, I'm not sure. Again, okay, we're not aiming for speed here, but here's what I would like to say. So there are two ways to approach your problem in general. If you would like to find x and y. So there is the first method, which is called elimination. And this is really best illustrated by an example, because I don't think there's any theory that will help you understand it more than this example. So if I write down my two equations here, minus x plus y is equal to minus 3.5, and x plus y, okay, 3y, is equal to 9.5, then elimination involves eliminating, okay, this is self-explanatory, but eliminating one of the variables. So here we can actually eliminate one of the variables without doing any effort. And yeah, so Isiosius just pointed this out. We can add equations to equations. So we can't just so if this is equal to this, and this is equal to this, then this plus that is equal to this plus that. That's really the concept behind it. So you can add and take away equations. And as Isiosius suggested, you can add these two equations. 9.5 minus 3.5, I think, is 6. No, yeah, 6. And notice that this is very nice, because the minus x cancels out with the x, gets 0. Because minus x plus x is 0. And y plus 3y is equal to 4y. Now, if 4y is equal to 6, then clearly y is equal to 6 over 4, or 3 over 2, or 1.5, or 3 halves, or so on and so on. So here it is very straightforward. It's a nice clue to know. And if you can spot the two equations quickly enough, and you see some factors which can be cancelled out, then you can even, for example, multiply the equation first by a constant, the whole equation, and then you would eliminate your variable accordingly. And we will see an example in a moment. Now, just for the sake of illustration, I would like to do this problem by a substitution as well. So by substitution, we basically solve one equation for one variable. So I think you pointed out that we would like to make y the subject. So maybe you would like to help me do it. You would not. Okay, that's fine. Maybe I'll just do it myself. My lonely self. Yeah. So this is the system of equations. I will take the first equation, and let's say I want to solve for y. Then this is not too tedious, because if I add x to both sides, I get that y will be equal to minus 3.5 plus x. Is this clear for everyone? Okay. You can always object to this, whenever you like. And then if y is equal to minus 3.5 plus x, then guess what? This is an equation which has x and y. So I can just, so if this is the first equation, this is the second equation, then it's like I'm plugging in 1 inside of 2. And I put quotation marks here because this is not rigorous. Effectively, what I would like to do is the following. So I would replace the y that I have here with the equivalent expression. So this is y, 3 times y. I would remove the y and put minus 3.5, okay, minus 3.5 plus x instead. Don't forget the brackets. And now we have an equation in one variable. So this is an equation in one variable. It's only one variable x, and it's only one equation. So we've reduced our system from two equations to one equation. You can, of course, feel free to expand this and solve it. And you can verify then that x will be equal to, well, if y is 3/2, then x is here, then 5 and 5. Then probably x is equal to 5, yes, minus 5. So minus 5. So you will get this, you get that x is equal to minus 5, and then you would plug in for y, and then you would get the solution. But I think we see now that it is much more convenient in this very specific case to use elimination. And it's just, you just need to give it a quick glance. And if you do so, then you're able to make progress on the problem very quickly, and then you gain lots of valuable seconds. Now, regarding word problems, if you have a word problem like this one, it's really just converting the word problem into a system of two equations. And then you do the standard work. So we will worry about this in a moment. Perhaps I would like to work on this equation. This system of equations, I'm sorry. So maybe you guys can get, I don't know, 30 seconds to do this problem. 30 seconds is much less than 1 minute. So maybe you can try it out yourself. And the solution here requires a very clever trick. So it's not tedious, it just needs you to give it a quick glance as well. And it involves the same skill that we've just discussed moments earlier regarding adding and subtracting equations. Maybe that's a hint. Bless you. So I think the 30 seconds are done now. And you guys are probably working on the problem. I appreciate all the
No,
effort.
it is -5. You can just subtract those two equations. It gives you like 3x, 3y, and then 5. -5, sorry.
Okay. Yeah. That's the way to go, actually. Thank you, Lucius. So this is the first equation. Now, the second equation is 4x minus 8y is equal to 9. I would like to know what the value of 3x plus 3y is. Here I see a golden opportunity, because if I look at x, and this is what I want you to focus on, then I have the coefficients which are 7 and 4. And clearly, if you take away 4 from 7, then you get 3. So that is already a Q. You just give it a quick glance. You see you want 3x plus 3y, of course, but let's focus on 3x for now. Then it is 7x minus 4x. Then maybe I should take away both equations and see what happens. Okay, maybe I shouldn't do that immediately. I should also give a quick glance at the coefficient for y. So here we are lucky. I see we have -8 and -5. if I take away -8 from -5, okay, this is counterintuitive. Yes, then I'll get 3. I mean, minus of -8, and then it's just +8, and then you take away 5, then you get 3. So this is very nice. You get 3x, and you also get 3y. And on the other side, you just need to do 4 minus 9 equal to -5. So that is indeed the answer. That is 100% correct. And it's not the kind of problem where you would spend a lot of time on if you know what you're doing. So it's very important. Well, okay, to focus. Okay, it's a tough exam. You need to be focused. You need to be well prepared. So it's easy to say that you should focus and find it, but the reality is you just need to see it. You just need to see it multiple and multiple times. And then if you see it enough, you'll notice the pattern, you'll learn the skill, and you will apply it. So that is my advice for you. Now again, word problems. And this is also the same idea. This is a problem of the same style. So I don't want to ask about this value of xy. I want you to work on finding the solution now. So you have 30 seconds. Okay, 50 seconds. I think that's more fair to try and attempt. So maybe with a stroke of luck, we would be able to eliminate one of the two variables, and then it would be very nice for us. Yeah, I think that's good. Maybe I'll start writing down some notes myself. The first thing I would do myself is I would write down the equations in my own handwriting, so that I can get a grip for the equation itself. But then what? Then I would like to use elimination, and this is quite convenient because I can see initially now that here I have 5x, 5 next to the x, and 10 next to the other x. So if I just multiply by -2, let's say the first equation, and add it to the other one, then I should be able to eliminate x. So
eliminate y.
Or you could do the same thing for the second equation. You could do any way you want, and it will give you the same answer. And that's what's amazing about it. So let's try this this method, I'll multiply this by -2. So if I multiply this first equation, -2, I get, well, 5 times -2 is -10. And 14 times -2 is -28. And 25 times -2 is -50.
That's supposed to be.
Ah, I copied it incorrectly. Okay, amazing. Then 45 times 2, I think it's -90. Okay, then this is a true statement, and I know it's a true statement. And if I add both equations to each other, so I go from here to there, and then if I add these two equations to each other, then 10 and 10, -28 plus 7, that's -21y, which will be equal to 90 minus 27. I think that's 63. Then this means that y is equal to -3. And if y is equal to -3, then I can just plug, let's say, plug in -3 in here. So I get 7 times -3. So it's -21. So 10x minus 21 is 27. And in that case, x would be 4.8, if I'm not mistaken. Can somebody verify this? Maybe I should show work if you're not following.
Isn't it to doesn't it have to be like -63 because like -90 plus 27?
Ah, yes, you're right. Thank you, Yusuf. Yes, you're right. So it's -63. I forgot to put the minus. Thank you for pointing this out. Okay, in that case, then we would have a different x, because I would now replace y with 3. So 7 times 3. Then we have 21 is equal to 27. Then the 10x is here. Then 10x is equal to 6. Then x is equal to 3/5 or 6/10. So that's just one way to do it. Now, can somebody also verify that this will be the answer? Yeah, 0.6. 3/5, 0.6. Okay, but what is the question really asking us? It's asking us to find x times y. So in that case, x times y would be 3 times 0.6, which will be what? It will be 3/5. 0.6 is 3/5. 9.8. Yeah, 9/5 or 1.8. So I hope you notice also the skill of plugging in the value. That's very crucial here. We don't dive deep into it because it's not the core focus of our discussion today. But yes, so we get 1.8 as the answer for the question. And this would save you a lot of time because if you start solving for y, or if you start solving for x, then you have to. It's a whole nightmare. Like, I don't even want to start talking about it. And now I want to discuss solutions. So when we talk about solutions to equations, I would like to look at some examples. So today we talked about how lines can be intersecting at one point, how they can be intersecting at every single point, and how they can be intersecting at no point at all. So here we would like to find the C which would make these two lines not intersect at all. In our case, we are lucky because we have solved for y. So this is a very special case, guys. Usually it's not like that. Much more tedious. And because it is in y is equal to something, then I can probably plot it. So there's a y-intercept at 8. There is another y-intercept at 10 for the other line. You still need to choose its slope, so I won't draw it. Maybe I'll use some colors. So in my mind, this is the brown line, and this is maybe the purple line. So this is this equation. Now, if you want to plot this equation, I think this is y is equal to x, then y is equal to half x probably looks like this. I'm just guessing that. So please don't be harsh. So this is supposed to be the drawing of y is equal to half x plus 8. So it's increasing because the slope is positive, and it has this y-intercept. Now, what is the way that I would make it have absolutely no solution? This system. What do I need to do with the other line? I don't want to have any solution. So I don't want to have any x and y which satisfy both equations. If you remember, this is what we were discussing. Okay, here. So on the right, but they never intersect. Okay, maybe I'm literally pointing at the solution. But what I want to say here is you have two lines which do not intersect at all. So there's no x and y which lie on the same line. Now, if x and y lie on this line, then they satisfy the equation for the line. And so if there are no 2 points which lie on this on both of, if there's no point which lies on both of these lines, then there's no point which satisfies both equations. Then there is no point of looking for the solution. Yeah, I have to show it. Sorry. That's a lot of no points. So this is clear for you. And if you look at this now, it's just a case where you have them parallel to each other. So we would like to have them parallel, meaning we would like to have them with the same slope. So if we choose the value that gives us the same slope, then we are done, right? So there you go. Can you tell me what this value is going to be?
I think x should be 0. Or the value of c should be 0. I don't know.
The value of c should be 0.
1/2, because like R has to be like the same slope.
So I would like to start first with Flavia's suggestion. So y is equal to 0 means that c is equal to 0 means that straight line, right? So this is an amazing moment to stop and say they actually intersect. The only way they won't intersect is they have the same slope and a different y intercept. So you would do like this. You would go a little bit upwards. And then you know that these two lines would never, ever, ever intersect. So if I choose C to have the same slope, which is half, as Isiosius just pointed out, then I'm done. Done. There's no way these two lines are meeting. And I think everybody agrees with me on this. If somebody disagrees, I mean, please feel free to step up. And we can talk about it. We can have a very nice conversation about it. See you. Okay, now another one. See you. Goodbye. So this is more or less the same idea. We have two lines, and luckily we have the nice format that we like. We know how to plot. So what these things A should be if we want to have no solution. 2, and that's not too difficult. We were just talking about this. So you are right. A should be equal to 2 because they have the same slope and they have a different y-intercept. So it probably looks something like this. I'll just briefly sketch this. So probably there's a -8 here. This is probably -8, and probably there's a 1 there. And since they're parallel, there's absolutely no way that they'll meet. That's really what it is about. So you've just solved a hard problem in what? 2 seconds. And if you keep on doing this in the exam, then you'll be done very early on. And that's really the idea. It's not really about putting lots of effort. It's really about having the right knowledge and being able to apply it in the right time. Okay, this is an equation with no solution. I don't think it would hurt. Okay, maybe it would hurt if you look at it. So I need to find another problem because we've been doing lots of no solutions. I want to do one of the problems where you have one solution or where you have an infinite number of solutions. Yes, like this one, for example. So this is an equation that is in the quote-unquote bad form. So we don't like this form. We're not quite sure how we can plot it. We need to solve for y first, and then we know how it looks like. But nevertheless, this is no huge issue. Now, again, if you want this system to have an infinite number of solutions, then you would like to have the same 2 lines, or you would like to have 2 equations in this case that are linearly dependent.
Yeah,
Is the answer 1 by 2? I'm actually not sure. Let me see. So 1/2 plus y is equal to c.
they're intersecting at 1.6, so
Mm-hmm.
basically the same.
So I think
Isiosis, I think, has a suggestion.
so like, I think it is like D, right? 3/2 because so like I was thought like if you like 1/2/a equals to 1/3 over like the coefficient of y, but it does have coefficient, so we have to multiply it, the second equation by 1/3 all of them. So that gives us a/3. 1/2/a/3 should be equal to 1/3 over
Okay.
yeah.
Okay, I see.
So
I see.
1/3
Yes, that's a good suggestion. So, Singh, do you agree with me that we would like to have the exact same equation?
can you hear me?
Yes, I can hear you, Isiosis. I heard your solution. It's good. We will talk about it in a moment. I'm just discussing with Singh now.
I
Okay.
think my network.
You hear us, right? 1, 2, 3, 4. Do you hear us, Isiosis? Don't hear you if you're talking. Saying something. Well, anyway, so back to Singh. We would like to have 2 equations which are
I
exactly.
think I'm having a problem with my network.
Oh, no, it's fine. But I heard you. Your answer is good. Okay. So 1/2 of x plus 1/3 of y is equal to 1/6. Okay. If you choose a, as you just said, to be half, you have 1/2 of x plus y is equal to some c. But this is a problem, because if this is half, then this probably also should be a third, right? So probably this is not the solution because it gives you a different equation.
There's no one.
Yeah, so this is why it's not the solution. So we want to have the exact same solution. And if you want to do this, then the idea here is, you know, it will be the same. So you know that this third, no, not the third. So if you make y be equal to y, then x will be equal to x. So my idea here would be just to multiply by 3. And here's the magic that happens. So I have 1/2 x plus 1/3 of y is equal to 1/6. Okay. Then I multiply by 3. If I multiply by 3, I get 3/2x plus y is equal to 1/6. No, 1/2. Okay. Then here's what happens. Yeah, so we know that we want to have an infinite number of solutions. So we assume that they are the same line. So we assume that this equation is equal to that equation. It's equal to ax plus y is equal to c. Then, if I choose a to be 3/2, the coefficient of y is the same as the coefficient of y, and the coefficient of x is the same as the coefficient of x, and the constant we don't need to worry about. Then we have the exact same equation, and we can say, yes, this will give us the exact same equation, which will have an infinite number of solutions.
If we multiply by 3.
Here's why. So first off, you agree with me that the two equations should be exactly the same. Then the coefficient of y should be equal to the coefficient of y. No, sorry, my apologies. If the coefficient of y is equal to the coefficient of y, then the coefficient of x should be equal to the coefficient of x. Sure, go for it.
Equation ax plus y is equal to c. If you make y the subject, you find out that it's the same equation of a line, actually. So for the first equation, you could make y the subject, and by doing so, you realize that x will be 3/2x plus 1/1/2, which is equal to the equation of the formula.
Yeah, but you still need to solve for the, so you need to set it up in this form for both of these,
Yeah,
for those of these equations.
for both, for both equations, you set it basically like the way the equation of the line is, which is equal to y is equal to mx plus c.
Yes, that's the nice way we have, but usually it's not like that. So we want to be able to also maneuver ourselves when we have equations which are not specifically of this form. You get me? But this is a good way to look at it. So actually, this is very close to looking at to look like the equation of the line. If you just manipulate it, this is a third of y, this is y. Then you just multiply by 3, and then you compare the equations, you compare the slopes. But in general, the slope is always the coefficient of x. No matter what you have, the slope is always the coefficient of x when the coefficient of y is equal to 1. Now, if the coefficient of y is equal to the coefficient of y, then the coefficient of x should be equal to the coefficient of x because they're the same line. But let me give you an example of two equations which are the same. I think this is the last thing we should do before we leave. So I can take, for example, y is equal to 2x plus 3. I will multiply this by 2. On both sides. Then these two lines are really just, well, I don't want to say equal, but I want to say are giving the same data. let's say info. They're giving us the same info. Let's say I take 3y and 3 of this. So I multiply both sides by 3. It's the same equation. It has the same amount of information. So it's really just one equation and one line. What's your favorite number? 10. Okay, I also like 10. Then you can just choose 10y and then 10 times 2x plus 3. And similarly, you can choose any constant and you can multiply your equation by, and then you know that this will give you the linearly dependent solution. This is what I mean by linear dependence. So the equation is a linear factor of the other one. These two equations are linearly dependent, and I can do this for any any constant. And I think this is very good for today. Thank you for joining me, and it's been an absolute pleasure. And I'll be here if you have questions. Yes. Am I what?
I'm in B2.1 gym. Yeah.
Yes, I sit next to you. Yeah. How did you not notice it?
I thought you had a 2.
No, I'm the same person.
Choose.
I'm sorry?
Choose.
Who's? Who's?
See you on Monday.
See you, goodbye. Maybe it's a good time to stop.
Bye bye.
Bye bye.
And